Assalamu alaikum Chem 20s for the online class specifically. What we're going to do is we're going to introduce you to stoichiometry, and this is probably one of the most used / most important concepts or skills that you're going to get from Chemistry 20. In fact, you're going to see it in Chemistry 30, used in multiple units, and as well in first year university. So it is important that if you find this video is going a little bit fast, you pause the video, rewind it back, and then rewatch it so you catch up with all the concepts. So what is stoichiometry? When we say stoichiometry, what we really mean is we're essentially looking at the math, the main math that's involved in chemistry. And this math is based on two things. The first thing that it's based on is the balanced reaction. So in grade 10, when we were balancing reactions, the idea was that we were eventually going to use them for stoichiometry and to predict how much we're going to get if we do a certain reaction given certain amounts of reactants in a lab setting. So it's based on a balanced reaction, and from the balanced reaction, it's based on something called the mole ratio. Now, what the mole ratio is really telling you to do is to treat balanced reactions like recipes. And so let's say I have the formation of water. And we're going to do water vapor. We'll say that this is in an open system. So we'll create water vapor. Now, when I balance this, and I'm going to do this rather quickly, if you want to see if you can balance this yourself, I suggest you pause the video, balance it, and see if you got what we get in this video here. When I balance this out, we end up getting 2 moles of hydrogen gas plus 1 mole of oxygen gas gives us 2 moles of water vapor. Now, what we're really saying is if you think about a recipe, for example, making pancakes, you would say that a cup of flour plus a cup of water or milk plus 1 egg is going to give you 6 to 7 pancakes. And so it's a 1 to 1 to 1 ratio. And if you change the amounts, if I double, let's say, the amount of eggs, flour, and water, then I'm going to get double the amount of pancakes. Well, it works the same way with these balanced reactions. Now in grade 10, not grade 1, grade 10, when we were balancing reactions, these coefficients here, and there would be an invisible one, right where the oxygen is, these coefficients didn't really mean anything other than the fact that we were just trying to make the number of atoms the same on both sides. Now, these coefficients are going to represent the number of moles that are required by each entity. So the coefficient equals the number of moles. And so when we read this chemical reaction, what we're really saying is that 2 moles of hydrogen is required per 1 mole of oxygen in order to produce 2 moles of water. And so the coefficients now mean the number of moles. Now, what the mole ratio is that it compares 2 entities in a balanced chemical reaction. Right? So it's a comparison of 2 or more entities in a balanced reaction, and in order to compare, we're going to use these coefficients right over here. And so, for example, let's say we asked you for, and we'll do an example over here, what's the mole ratio between, and we would have to get specific on what we're mentioning here. So between, let's say, H2 to O2. So that's 1. And we'll do another one here. We'll say H2O to H2. Well, when we refer back to our balanced chemical reaction, we see that between H2 and O2, there are 2 moles of H2 for every 1 mole of O2. So we would write over here 2 to 1. The same can be said when we look at H2O and H2. We can see from the balanced reaction that there are 2 moles of H2O to 2 moles of H2. And so when we write the mole ratio, that's 2 to 2. Now, what if I reversed it and I said, what about from O2 to H2? So we're going to look at this mole ratio from O2's perspective. Well, going back to the balanced reaction, we would see that when we compare O2 to H2, it's 1 mole of O2 to 2 moles of H2. So we would write it as follows, where it's a 1 to 2 ratio over here. Now, this is pretty straightforward when we have a balanced reaction and we use the exact amount of moles that the equation or the balanced reaction outlines for us. However, the key question here is, because it is very rare that you're going to have exactly 1 mole or 2 moles of a substance. Those are actually very tiny amounts, and often you wouldn't be able to actually use that amount. That would almost be considered, nano amounts. What happens when the amounts change and they change into something, okay, that is more usable or more realistic in terms of a lab environment? So what happens when amounts change and we increase these reactants to a more usable amount in a real world setting? Well, this is when we're going to need stoichiometry. And remember, just like in making pancakes, the recipe amounts, right? So the amount of flour to the amount of eggs and to the amount of water is going to be set. And so just like that pancake recipe, when we look back at a balanced reaction, the amount of H2 to O2 to water is set. So when one thing changes, the other thing changes as well. So once we change any amount in the chemical reaction, we're going to need the stoichiometry formula. So in order to predict how much you need of a reactant or how much product you're going to produce, once we have changed the amount in the lab setting with reference to the balanced reaction, we're going to use this question here, this equation. The stoichiometry equation is the given in the question. So when we tell you, for example, 2 moles of chlorine is reacted with sodium, well, that 2 moles is the given. It's the information that they're giving you as you read through the question. So given in question multiplied by the required. Now this required is what we're trying to find. So when I ask you, given that 3 moles of Cl2 reacts with sodium, how many grams of sodium chloride are going to be produced? Well, that how many grams of sodium chloride is going to be our required. And then there's this weird part of the equation where it says given in chemical reaction. What I'm going to do here is highlight a couple of things in this formula. First is that it all needs to be in moles. So everything you see in this chemical reaction from this bracket to this bracket is all in molar amounts. The second thing that we're going to underline here, or highlight, is that this and this, the two givens here, and we'll connect them as follows, they're going to be the same substance. So if the given is H2, then the given in reaction part of the formula over here is also going to be H2. So the same substance, but different amounts. And you'll see how that works, but we actually plug it into the equation. So the same substance, but different amounts. And so when you're solving this, make sure that this and this is going to be the same. And lastly, okay, this section of the formula over here, so this entire section, this is the mole ratios from balanced reaction. And so key things to remember is that everything has to be in moles here. The givens have to be the same substance, but they're going to be in different amounts. And the required, written in purple, is always what the question is asking for. Let's see exactly how this formula works when we're given an actual question. But before we do that, we need to outline a strategy in order to solve stoichiometric problems. So here's just a list of 3 simple steps that we're going to apply to each stoichiometry problem until we're very comfortable solving them. The first step is that whether I give you grams or kilograms, you're going to convert all given amounts to moles. And we're going to do that using that very valuable triangle, right, that we did in grade 10. The second thing is, once you've converted all givens to moles, we're going to use that stoichiometry formula that we just previously described in order to solve for the required, right, whatever the question is asking for. Lastly, and this may not be the case for all questions, but if they want to know the mass of something, right, the mass of the required, well then we'll just convert the required in moles to the grams, once again using that special triangle. And the special triangle that we're referring to, in case you don't remember, is this one here, where it's grams is equal to moles multiplied by grams per mole. And remember that the grams per mole is really the atomic mass from the periodic table. Okay, and so this triangle shows all the relationships between these 3 units. So let's get to solving a question. So the first question says, from the following reaction, how many moles of H2O are produced if 0.176 moles of O2 are used? So what I'm going to do here is, remember, I'm going to underline the coefficients, because those tell us the moles that are needed, or the mole ratios of each of the entities involved in this chemical reaction. And we're going to use these coefficients in the right side of the stoichiometry formula. So the first step tells us to convert all givens to moles. Well, the given, first of all, let's identify that. That would be the 0.176 mole of O2. Now, we don't need to convert this to moles because, as we can see here, it's already in moles. So first step is going to be done. Now the second step, which is probably the most important part, it says to use the stoichiometry formula in order, okay, to find the required. So in this question, the required, and I'll write it down over here, is how many, when you look at the question, how many moles of H2O? Okay, that's the required. And so we're going to use the stoichiometry formula for this part over here. And remember that the stoichiometry formula looks like this. So we're going to translate this formula over here into real numbers with everything that's been given from this balanced reaction in the first place. So the given in the question is going to be our 0.176 moles of O2, because simply that's what was given. So we're going to plug that in here as follows. And then we're going to multiply it by the required. Well, what is the required? The required is how many moles of H2O. So that is going to go on top. And remember that this and what goes at the bottom here is the denominator are going to be the same substance. So we're going to write O2 as well. Now, this section on the right is going to refer to the mole ratio. And when we look at the mole ratio between O2 and H2O, we can see that it's 5 and 6, which means that it's 6 moles of H2O to 5 moles of O2. Now, for those that are math savvy here, the O2s would cancel out, and all you'd be left with is the amount of H2O. So when we plug this in our calculator, we're going to go 0.176 moles multiplied by 6 over 5. And when we plug this in our calculator, we end up getting about 11.33. Sorry, not 11.33, that's a mistake. My apologies. It ends up being about 0.211 mole of H2O produced. Our second example reads as follows. The reaction of calcium with water can be predicted using the activity series. What mass of water is needed to completely react with 2.35 grams of calcium? So first thing that we need before we even start any of this is a balanced reaction. So we're going to go calcium plus water is going to give us what? Well, remember that this is a single replacement reaction, and we know that because we have A, B, and C. Now this water, remember from the beginning of the year that we said that there's a little trick when it comes to water. That whenever it reacts with a metal, it is best that we write it as HOH. And when we write it as that, then that makes our H the B and the OH the C. And so when we complete our reaction as a single replacement reaction, remember that A plus BC gives you AC plus B. And so that would give us calcium combining with hydroxide. Now calcium has a charge of 2 plus, and hydroxide has a charge of negative 1. So when they swap and drop, we're going to get this. Which leaves then B all by itself. The hydrogen. Now remember, hydrogen is a diatomic element. So when it's by itself, it's going to have a 2. Now remember, when we swapped and dropped this, it came from the charges, not the subscripts. Always swap and drop the charges. So when we balance this, we end up getting the following coefficients. Putting a 2 in front of the water gives us 4 hydrogens in total on this side, and then 2 oxygens on this side. 1 calcium, that's fine. And then of course when we look at this side, it's 2 oxygens, 2 hydrogens, but then plus another 2 gives us 4. And so everything balances out over here. So this is going to be our working reaction for this Stoich problem. Now, remember that the first actual step is going to be to convert all given amounts to moles. So what we're going to do is we're going to convert 2.35 grams of Ca to moles. And we're going to do that using this triangle. Right? With the grams per mole, and then moles. And when we solve for our moles, it's going to be, according to the triangle, grams over grams per mole. Which when we plug in our values, it's 2.35 grams divided by 40.078 grams per mole. And this comes from the periodic table. And when we plug that in, we end up getting about 0.058635 moles of calcium. So now we've got our grams of our given substance here. The next step is to move on to the stoichiometry calculation. Now remember, stoichiometry calculation is going to be given multiplied by the required over the given in the chemical reaction. The given is going to be this amount over here because that is essentially what is given in the question. Although they give it to us in grams, we converted that to moles. So we're going to go 0.058635 mole Ca solid. Oops. Just change that over here. It's going to be multiplied by, now what we're trying to find when we look at the question is asking for what mass of water, this over here. So we're going to write H2O on top, since that is the required. And remember that this and this at the bottom of the denominator here must always be the same. So this will be calcium. We're going to go back to our balanced chemical reaction, and we can see that it is 2 moles of water for every 1 mole of calcium. So our mole ratio that we're going to plug in over here is 2 to 1. Again, those that are mathematically inclined, we know that the calciums cancel out, leaving us just with the amount of water here. And so when we plug this in to our calculator, we end up getting as follows. And that gives us about 0.11727 moles of H2O. Now the problem is when we look back at the question, it actually asks for what mass of water. So then this here becomes a step 3 question where we take the amount that we calculated in moles from the stoichiometry, and once again, using this triangle over here, we're going to take our found amount and convert it to mass, and that'll be grams is equal to moles multiplied by grams per mole. And the moles in this case are going to be 0.11727 multiplied by the grams per mole of water. So that's 2 hydrogens and an oxygen, which ends up being about 18.02 grams per mole. If you want to take a second, pause the video and recalculate that yourself, you're more than welcome to. And finally, when we plug this in the calculator, we get about 2.113. We didn't ask for any specific digits here, so we're not being picky. We just want you to get the concept. 2.113 grams of H2O required. And so that really sums up stoichiometry. And again, it's one of the most required skills. So what I urge you guys to do is to stop this video, go and try the ones that are posted on the Google Classroom yourself, and let me know if you have any questions. Assalamu alaikum.